Well, hello everybody, and welcome back to the bench. So, I want to go over a few things before we kind of reveal our next project. And a couple things. First of all, lots and lots of comments on the Silver 9Ts, the Carver Silver 9T amplifiers that we did. And I promise that I will definitely get a demo out of those amps, and at that time I will try to answer some of the comments and so forth, because a lot of really good things. I never realized those amps would bring that many comments and so forth. It's really cool. So yeah, just stay tuned, and once we get those JFETs swapped out in those amps and finish the final alignment and everything, we will definitely get those up there and do a little audio test and answer some of the questions. One thing I thought would be really interesting for you to see, though, is this little can with capacitors. This is all of the capacitors for two amplifiers, both amplifiers. That's all. That's all that's in that. I thought that was pretty impressive. That's really all there is in these things. Now there's a huge semiconductor count in those amps, but as far as electrolytics, very few. Another thing is, I've never really heard of some of these names that they use on these caps. This Precon, P-R-E-C-O-N. But whatever, maybe some of you have heard of them. Every single one of these, look how clean they are. They're just absolutely perfect. And I just randomly tested several of them, and I have yet to find one of them that's bad. I almost wonder how long these would have lasted had we not recapped it. Obviously, they're 30 years old, so they should be replaced. But it's just kind of, again, another one of those surprising things you find out about these Carver amplifiers. The components are nothing that you've heard of before, yet they seem to be good quality components. The way that the circuit's designed and put together would make you think that, why would you do, like, ganging up transistors in parallel like that without any just the way it's done is, but then you put it all together and somehow it works. So this was a very interesting project for that reason. And I really enjoyed working on them. So thank you all for your comments. Here's the two resistors with the bulbs. Those will go back to the owner as well. And I promise I'll do a follow-up. Now, another thing I want to share with you real quick is I just got something in the mail. And this is from a fellow YouTuber. And if you ever get a chance to check his site out, if you haven't already, it's Mike's Radio Repair. And Mike over at Mike's Radio Repair is just a fantastic repair engineer on these things. He is so knowledgeable, especially with radio equipment. He works a lot with CB radios and ham radios, but all kinds of electronics, and every one of his videos is a little bit different and has something in it that you'll pick up. Even if you're an experienced electrical engineer, there's little things, and that's what I really like about people like Mike, is that they'll put things out there that you don't learn necessarily in college. They're little tricks and tips that you learn from experience, and when somebody that's been at it a long time shares their experience with you, that's one of the best educations you can get. So thank you, Mike. He sent me this part because he's been following my video on the F28. If you remember the Pioneer F28, the Rube Goldberg tuner, we needed one of those TC9100 PLL chips, and it's slightly different. And I did email him about this, and he got back to me very kindly and explained that, in fact, this is very similar, with the exception of one or two pins, to a lot of the more common PLL chips used in radios. But this is different. And he had some of them in stock and was so kind as to send me one. So thank you, Mike. Thank you so much. And I recommend all of you check out his site, Mike's Radio Repair. So we will be getting back on this, although I don't know when, because there's quite a few other things I have in the queue right now that I really have to get caught up for people and get done. So without any further ado, we have something else here, and this is going to be our next little project. And somewhere in the middle of this project series, I'll probably do those Silver 9T demos, because those parts should come in. It's looking like I'm about a week or two off of getting those JFETs. They're not easy to find. Let me talk about that real quick. I'll keep you in suspense another minute. The JFET that's used in those 9Ts, I have the old one here, I think, handy, I can show you, is a 2N5458, and I don't know if I can get in there close enough to see it, but it's a 2N5458. And then there's also a 2N5457, and I think there's a 5456 as well. There's 3 or 4 in that series, and they're all very similar JFETs. They're all depletion mode. The main difference is the characteristics of the gate, the trip voltage for the gates and so forth. Here's an example of why it doesn't always work to use a replacement like NTE. If we go to the NTE app, so let's look at the app here. If you ever get a chance, you can get this little app on your phone or whatever, your smart device, and type in 2N5458. Up, and then the spell check does that. 5458. And if you notice, it crosses to an NTE 457. And if I change this to a 2N5457, okay, it also crosses to an NTE 457. So you can see they're using the same component to be a crossover for both of those. Now, if it was just a matter of, the one has a little higher voltage rating than the other, and the NTE one has the higher of the voltage ratings, everything else the same, you'd get away with that. But if you tried to use that component in that Carver amp, because of how critical the circuit design is on that, it would not work. You really need to get the correct one. The funny thing is, 2N5457s are very, very common. They're everywhere. Matter of fact, I keep them in stock. I probably have 20 or 30 of them in stock. The 2N5458 is not as common. And the main difference, again, is the gate characteristics. I mean, everything else is pretty much the same on them. And if you try to use, and I tried, a 2N5457, it will not properly open up the muting circuit. Because of that gate characteristic. Very critical that you have exactly the correct component, and that your replacement component, even though the part number is the same, has the same characteristics. And that happens quite often in some of this older equipment. It's so critically designed. We run into that a lot of times on some of the Pioneer gear you see. I can't just pull a transistor off the shelf and slap it into, for instance, a phono stage, or into the differential pair stage, of the front end of the power amplifier. It doesn't always work. It will cause the amp won't bias properly, or you'll get a distortion, or it will clip unevenly. And it's all because the component that you're replacing doesn't properly match the one, that you're replacing it with. So, I mean, even in the same batch, you end up having to test different components and so forth to make sure they match properly. And what I will tell you is, I did find a couple sources for the 5458s, the ones that I think will work properly, but they're on back order, and there was about a 1 or 2 week lead time, which is not bad, but we have to wait. So that's why the Silver 9T demo won't be for a couple of weeks. On another note, if you take a look at this, I'm still working with this little, now this is a little later revision of my little transistor matching device. And no, I haven't forgotten about it, and I haven't abandoned it. I have been using it, but I've just been kind of using it and observing the results before I release any more information about this. But it's very interesting how this circuit is working, and how so far I've been able to very accurately match the small signal transistors, the little NPN and PNP transistors, using this little device. I've added a little scope output and made it a little bit more simplified, corrected my little diode issue. There's no longer a need to toggle back and forth between PNP and NPN. It will actually work with either one. It doesn't care about the polarity or anything now. One of the reasons is we're now using an AC signal to to drive the transistors rather than DC, positive and negative. We'll get more into that later, but this might be something that I will talk more about, as long as it keeps performing the way it is. I'm just kind of comparing how, using this to match two transistors, or to compare two transistors with a more conventional method of using either the little peak unit here, like one of these, or using one of those little $8, test everything things that you buy on eBay, or using the curve tracer itself and matching the curves. I'm finding that this seems to jive with all of those very well. And it even shows you some things that those other test devices do not, because this gives you, just like the curve tracer, it gives you a very visual picture of what's going on the scope. So we'll get more into that later. But I just thought I'd share that with you and let you know this is not a dead project, and we're still working on it. Once we get to a point where I'm happy with what I'm seeing, then I've been offered by a couple people to maybe do a circuit board design so we could make a neat version of this on a circuit board, a printed board. And when that happens, I'll try to post that up there so that we can make these. So anyhow, let's move on now to the big reveal. Okay, so I figured, since we've already done a Rube Goldberg tuner, let's find a Rube Goldberg amplifier to go with it. So, behold, Rube's Cube. That's what I'm going to call this one, Rube's Cube. All joking aside, if you take a look, it's still wrapped up. This is how I received it. I don't even know if you could see through the glare, but it is an actual Carver M-400 power amplifier, magnetic field amplifier. Now this is a stereo amplifier. It doesn't hardly weigh anything, and it is rated at 200, I believe 201 watts per channel. Not 200, 201. And it shares a lot of the technology that we saw in the Silver 9T. It has the stepped rail, 3-stepped rail power supply. It has the triac-driven regulated magnetic field transformer. It has the same architecture for the output transistors. A lot of the things that you'll see, that you saw before, are going to look a little bit familiar in this. There are differences, but you can see the train of thought going through this whole, these two amps, how they're related to one another. Now, the first thing I will tell you is, when I got this thing, somebody brought it in. This amplifier has failed. Do not plug in. 5 power transistors removed. Power supply caps have failed. Other problems, missing hardware. So this is, I would definitely call a basket case. And whenever something shows up with transistors in a bag stuck to it, you know you're in for one. So this one is going to be a challenge. Now, the whole thing about the power supply caps failed, that's my biggest concern. These amps have a reputation that if you do not align the power supply exactly as the service manual tells you, it will exceed the voltage of the caps and it will fry your capacitors, and they're not easy caps to find. Again, Carver was pushing the limits of the components available at the time these things were designed. So a lot of his voltages are very high, and the capacitors that he would use on those power supplies would run very close to their maximum limit, voltage limit. And because all of this stuff was so compact and small, finding a component to fit in there, that's about all that was available back then. So if you misadjusted your power supply, the power supply can be made to exceed the voltage rating of the capacitors, and within seconds it could destroy the caps. And it says right in the service manual, you know, don't mess around with that or you will be sorry, you will damage the caps. So I think the way the book described it is something like you will cause the capacitors to vent or something like that, or explode or something. But bottom line is, every possible known problem that happens to these seems to have happened to this amp all at once. So we are truly going to try to put Humpty Dumpty back together again. And I don't know how successful we'll be. That's going to depend on how available the parts are, and I don't know if I'm up to the task. We'll see. We're just going to have to go through it and find out. But I think this will be an interesting little series, and I think this is a neat little one to kind of dovetail into that Silver 9T that we did. I'm sure these are a lot more readily available. They made tons of these. Actually, the little I worked in a high-end audio place called Custom Sound Company, but when it was called Custom Sound Company, I was not working there. I just went there a lot. But after the business changed hands, I actually worked as a bench tech at the company that bought them out. But they actually sold this amp, and I remember when it first came out, they had it connected to some speakers in the showroom, and there was so much hype about these amps that they were even misinforming the customer. I know the one salesman was a younger guy at the time, and I was really young at the time, so I didn't know. And he said, there's only one active component in this that for the magnetic field, that's all it uses. Well, I think what he was trying to explain was that this has that triac regulated transformer. And the way he worded it made it sound like there was no transistors, there was just this one active component that drove this special transformer, and the transformer somehow amplified the sound, which was completely and totally wrong. But it just goes to show how misunderstood these products were. I mean, we're talking about a salesman who was selling these, in a showroom for a high-end audio place, and he even didn't have a full understanding of how these work. So, but that being said, there were a whole ton of these out there, and you can probably still find them quite a bit on eBay or wherever. And so, maybe this video might be a little bit more interesting for some of you, because you may even run into one of these and decide to fix one up yourself. So I figured that would just, since we're on the Carver thing, we'll stick with it for one more project, and that's what we'll do. I remember these sounding extremely clean when they were brand new out of the box in the showroom, and I remember some of the speakers that they ran with these. I think they had, of course you have the speaker switching, so you can demo different speakers, but I heard these on a set of AR-18 speakers, I think, which are actually underpowered. This is a 201 watt amp, stereo, 201 per channel, and I think the AR-18s were only rated at 100. But again, this thing played really nice with those. set of Design Acoustics speakers, you know, those little cube, so they had the cube running cubes. They sounded fantastic with this amplifier. And then I heard them with a big set of tower speakers, and I can't remember what they were at the time, but this thing drove them pretty effortlessly. The thing I recall, and this was many years, 30 years ago, the thing I recall about this is that it was very clear and clean sounding, but it didn't have a lot of punch like some of the more traditional designs with the big linear power supplies. But then again, that was my perception at the time. This was kind of right before and during the audio CD was coming out, so vinyl was king still. But neat little amplifiers. So let's get this thing unwrapped and see what we're getting ourselves into. Oh man, I don't know if I want to open this thing. So until we can find a way to make smell go through these videos, you can't truly appreciate what I'm experiencing right now. I unwrapped that cellophane off of here, and I mean, I smelled trons. That's what we say in the industry here, at least in the X-ray industry. When something burns up and you walk in the room and you have that burning electronics smell, somebody says, "I smell trons." Well, wow, the smell that's wafting up from these little vents of burning electronics is pretty unmistakable. So I don't know what I'm going to get into on this, but it really smells. And do not plug in. Do you think they're like really worried about us plugging this thing in? I think so. Now, taking these apart is part of the issue. I think it's really, you can't really test things with it apart. So you have to do something, put these back partially together, test it, take it apart. So it's, believe it or not, working on this is way more tedious than those silver 9Ts. The 9Ts were actually very easy to get to and very easy to service from an access standpoint. This one, because of its small compact size, everything's crammed in there in one place. So wow. So let's let the rest of the smoke out, and I don't even have to plug it in to do that because I think it's still floating around in there. So we're going to open the covers and fan it out a little bit and try to see what all's wrong. Okay, so we have the covers off, and let me tell you something. This thing stinks. Looks like it's had a rough life. Now, I don't see anything in particular that's burned apart, and that smell could be possibly just a blown capacitor, a vented capacitor or something. I don't know. Although it doesn't have that cap smell. It has really a burning component smell. So there's probably somewhere in here is a bad transistor or something that we're seeing. Now, the way this thing's put together is you have two circuit boards, and you have an upper and lower, and really that's your right and left channels. So these two boards are pretty much identical. You have your power supply all on one board down here, and that's all there is to the amp. Here's your triac, again, very, very characteristic of the silver 9T, but a different triac they're using. Looking at the solder joints on this, some of this stuff's been replaced already. These caps, at least this one feels a little bit bulged up. This one does. They all feel just a little bit, maybe. So, I mean, a complete and total recap is needed on this, I would say. This transformer looks like it's seen better days. So the first thing we're going to do is we're just going to go through and just statically check with an ohm meter. We're going to check all these taps. Now they're numbered on here, so we really need to get a schematic out, and we can look at the taps and see at least if we have some continuity. We still don't know if it's shorted or whatever, but at least we will know if there's continuity, because if the transformer is blown apart, you're done, because where are you going to find that? It's not a normal transformer. So that's our first thing. The other thing that concerns me quite a bit is when somebody takes a Sharpie marker and writes the word parts. But then again, you know, this may be factory because it says AW, which usually stands for artwork 1.29. So it could be that that's factory, and that's not somebody telling you that this thing's completely hose bagged and doesn't work anymore. So let's just dig in a little deeper. Let's do the transformer first. Okay, the first thing I noticed that's pretty interesting is we have the opto-isolator circuit once again to drive the triac, and that electrically isolates the AC mains voltage from any of the control voltage. So these are very important. And normally we're used to seeing opto-isolators kind of like the 4N25 or things like that. It's like little 6-pin through-hole mount dip chip. But they actually, rather than using a chip, and I don't, maybe they weren't available or whatever, but as you can see, this is kind of a little, it's an opto-isolator, but they're actually using a light-dependent resistor and a light bulb, as opposed to an actual solid-state device. So they're showing that here, and they're calling it the opto-LDR, or light-dependent resistor. So instead of an actual semiconductor device, which would be like your 4N25 chip or whatever, they actually have an LED driving a LDR, which is, let's see if I have one. I'll show you what they are. At least I'll show you an example of one. Here's one. So here's an LDR right here. These are, let me get one out of the pack for you. So there it is. And what these do is they change their resistance. Come on, focus. They change their resistance based on how much light you put in them. So it is literally a light-dependent resistor. And then they just have that little light on the other side, and then it's just encapsulated in a little plastic tube, and they make it light tight. And rather than using a semiconductive LDR, whereas a normal opto-isolator will use a light-dependent transistor, that the base of the transistor is light-dependent, and it actually acts like a transistor. This one does not. So it's a little bit different. And of course they use, I believe, an actual opto-isolator chip in this Silver 9T. Now, getting to our transformer, we have all of these windings, and they tell you the colors of the wires, and these are all the secondary windings of the magnetic field transformer. And right there's your primary coming off of your mains. So you can see, now this one actually has a physical fuse in it, and you can see, so that's in there. And your thermal switch. So it has a lot of the same safety features as the other one. So there you go. So we're going to go ahead and we're going to measure these coils. Okay, so the first thing we want to do is you want to remove the wires from these coils before you test them. And the reason being is each set of windings that they're using has a bridge rectifier. So bridge rectifier from here to here, bridge rectifier from here to here, and bridge rectifier from here to here. And so because of that, if one of these bridge rectifiers is shorted and the coil here is open, a winding is open, and I try to read continuity, I will read the continuity through the shorted bridge rectifier, and I will mistakenly think that this coil is good. So you really can't test this in circuit. You have to remove the wires from the terminals so that you know that you're reading through these windings and not through a possibly shorted component. It will also give us the opportunity to check these at least statically for a short in here. We still don't know if these bridges are good or not, but we can at least check if there's a short from here to here. So just doing some static checking right now. So we have our meter and we have our wires disconnected, and make sure you mark them or you remember where they go or that could be a problem. So we're going to just start and we're going to go right down the line here. And the resistance should get progressively bigger, and it's not going to be a whole lot because remember, it's wire. It's going to act kind of like a short. And since they're all in series, you can see it's getting a little bigger. A little bigger, a little bigger. So good news. These coils, at least, I mean, there's no resistance measurements in the service manual, but I'm going to have to say that I'm going to have to call this transformer here, at least these windings, I'm going to call them good. So now we're going to have to check the other side, and to do that I'll have to get those disconnected as well, or at least partially disconnected. So let's do that next. Okay, I checked this one and it's good, so we put it back together. And now I'm going to check these ones. Now I don't want to take all this insulation off and have to redo that. But if you look, what's happening is this pink wire on this side goes to this terminal right here, and the green wire goes to the triac, so I can just disconnect one leg from the triac and I can get my measurements right there. And if I check right here, I'll show you. It's good. So far so good. The transformer is good. That would have been the deal breaker right there. Most of the rest of this we can fabricate or come up with a replacement to repair it. But if that transformer was bad, unfortunately the amp would no longer be repairable. So that's done. Now this triac concerns me because there's a lot of solder blobs on it, and I can tell somebody has had it out of circuit before. I don't know if it's been replaced or if just somebody disconnected it to test it, but it's definitely been, this is not factory work here at all. You can tell. The rest of it, I don't know that anybody has had a part yet, but of course we won't know till we get into it a little deeper. These amplifier modules, if there's a problem on them, that's where all the trouble comes in, because you can imagine taking all of these out. You have to take all these little screws out here, take all the transistors out, take these 4 hex standoffs out, and decouple these transistors to be able to pull the amplifier out of circuit or out of the thing to work on it. And then you have to make your repair, and then you put everything all back together. And all right, there's another bad part just talking to you guys. You see it? We have a fried resistor here. So this is going to need rebuilt, obviously. We have problems. And we'll have to look this component up to try to see what is in line with this that would cause this to blow. And I'm sure any of the associated components. Now the only thing I want to try to avoid is any of these strange transistors like these. Some of them, the modern replacements that are available may or may not be suitable or may not work properly. You'll have little intermittent problems or little quirks. You know, I know I get a lot of comments, why don't you just replace every transistor and everything all the time? Well, if the factory original components were available and you wanted to do that, I guess you could. But in my experience, whenever you replace a transistor, that should be a last resort. Because if it's working now and there's no leakage and it's fine and it's held up for this many years, chances are, as long as you replace the components around it with solid components that don't have any kind of problems with them, that transistor will work just fine for a long time to come. Anytime you replace one of these, you run the risk of something not matching properly. Transistor gain is a very, when these things run in their linear region, it's a lot more complicated than just slapping in a transistor. And even though you may have a chart that says you can use this one from this, parts house in exchange for this, that's only in certain circumstances. It's not in every single circumstance. And I've run into that time and again. And therefore, I do not just replace these unless I feel that it needs it. Now, where I will replace them is, say this one is bad, I will put the same component on the other channel. Once I find a good suitable replacement, I will put the same components on the other channel. So once again, the two channels are identical. That's the only time I'll do something like that, where I'll replace a component that doesn't need it. Now, capacitors are a different story. They have a life expectancy, and because they physically, the chemicals inside of them will change with age and dry out, and it is a known fact that they will eventually fail. Semiconductors aren't so easy to quantify that. Some of them can last many, many years. I have old germanium transistor components that have been working for many, many years, and they still work perfectly. We see this, in the X-ray industry a lot. I have machines that were built in the late 70s, early 80s that have original components and are still working like the day they were built. So, these components can last. Just depends. So, all right, let's dig in a little deeper. We're going to have to get into this power supply before we do anything else and kind of find out what all's going on here. So, I've worked on CAT scanners, X-ray machines, various types of stereo equipment. I've even worked on those cardiac cath labs, biplane digital cath labs from the 1980s that had rooms full of racks of equipment. And I have to admit, this disassembly will rival anything I've ever worked on before. Taking this thing apart, it's just like taking an artichoke apart. You just peel the pieces off and off and off, and when you're done, there's nothing left. But I guess the biggest thing isn't getting things apart, is it? It's putting it back together. So that's really where the proof's in the pudding, huh? So, well, we finally got the power supply apart, and yeah, as you can see, you probably cannot test this thing without putting it all back together. So really, we have to do our tests like this, and then rebuild it, put it all back together, and hopefully it works. If not, it comes all back apart again. And that's the problem with this amp, and I've read a lot of people who cry the blues when they have to work on these because of this. But anyways, it's just something you have to do if you want to service these. So we're going to start with the power supply. We're going to go through it, replace all the capacitors on it, test all of the semiconductors and resistors. Let's see here. I don't see anything physically burned or damaged on the board itself on the power supply, although the message was that the capacitors are vented, are bad, so we'll check those. We're replacing them regardless. These ones are doable. They're 4,000 microfarads, although they are at 80 volts, but I think I can find those that will fit in there, and we'll just have to go from there. Well, I've already encountered my first problem, and that is, let's take a look at this board for a minute. Let me zoom you right on in. If you look right down in here, you can see it's marked plus. There's a little plus sign there, and it's really hard to see in the light, but there's a minus sign right there. And this capacitor was oriented this way with the writing side up, and if you look, plus and minus. So this capacitor was installed backwards. Now, Was it installed backwards just because they tested it and slammed it back together and just kind of left it alone? Or was, now this one's in the right way, you see plus, plus, but this one's in backwards. So did they get the amp fixed and then put the part back in backwards and that's what blew it up? Or did they just get frustrated and just threw everything together just to sell it and got rid of it? We don't know. But we do know this cap was in backwards, and if they turned the power on with this in the way that it was, you almost certainly damaged it and damaged a whole lot of other stuff along with it. So, yep, someone's been here before us. So here's the supposed bad cap that was in backwards, and you can see it's got very low ESR. Now, not only is the ESR testing very good, but I put this on the LC53, the Sencor, and I actually applied 50 volts to it. It did have some marginal leakage, but nothing out of the ordinary for this size and age of cap. And the capacitance was reading about 33 to 3700 microfarad. It's reading a little bit low, but it's still reading capacitance. It would be what I would expect for a capacitor of this age. So this, even though it's a little bit degraded because of its age, is certainly not the cause of the problem. And I believe that this cap was taken out to test and they just put it back in just to get rid of the thing. This cap, though, is technically, I wouldn't call it good, but I wouldn't call it something that would cause a problem. There's no shorts in it, and it doesn't have excessive leakage, and it does have enough capacity to filter out the power supply. Okay, I have the other capacitor in there, and you can see it's reading 3,930 microfarads for a 4,000 microfarad capacitor. I'll call that good. The ESR was even better than the other capacitor. It was extremely low. And if we do leakage at 50 volts, I only have 50 and 100. I don't have 80 volts. And it takes it a while to charge up. And then you see it'll start out at higher leakage, and then as it charges, the leakage should drop. And if we get down around the 2,000 microamp, you know, it'll keep creeping down slowly after that. But usually if it gets down there on this size of a cap, there's nothing wrong with it. And you can see it's dropping down. And this is with you know, 50 volts applied to it. So see, we're well into the 2000s now, and it's still dropping. See there? So these capacitors are technically functional. I mean, they're good. They work. Again, they may be a little bit degraded, but they will not cause a problem with this amp. Maybe a little bit of in the performance thing if you want to make sure this thing's running at its peak performance, but these will not cause problems with the amplifier. So we can safely rule those out. Now we haven't checked all these little ones here, these little 2200 microfarads, but we'll remove them next and test them. Of course, I will replace these for what they cost. But again, I don't believe these are the problems. So here's something you don't see every day. We have a bridge rectifier on this side, just a full wave bridge rectifier. And if you go on the back of the board, fabric cobbled bodged onto here is a second one in parallel. Now, anybody in this industry would tell you it is an absolute no-no to put diodes in parallel like that they don't work that way. Why was this done? I'm not sure, unless maybe they felt that this was a failure item because it's too small, and so they put two together, but that'll never work right. The proper thing to do would have been to put a larger capacity bridge rectifier that has a higher current. Now the strange thing is that looks to be an afterthought, because this is the original schematic of the first release of this original power supply. And if you look here, originally the plus and minus 25 does not have 2-bridge rectifiers, but on, and I didn't print it out yet, but on the later model power supply, the 25 volt plus and minus 25, they actually show on the schematic that they literally ganged 2-bridge rectifiers in parallel. These are the things on Carver designs that kind of make me scratch my head. You know, why would you do something like that? I mean, you can only say it, you know, it's an innovative design so much on certain things. And in some cases it is an innovative design, but in something like this, I just can't possibly, other than it would require too much redesigning of the original power supply. But again, I'm sure I could find a bridge rectifier that somehow would fit in there with a higher, you know, this maybe is a 4 or 6 amp bridge at this physical size. I don't know, I didn't look the part up. But you know, a 10 amp one isn't a whole lot bigger physically than this. Maybe at the time they built these it was, or that parts weren't available for that. But again, you just don't do it. Yeah, I've never seen a commercially designed power supply that had bridge rectifiers in parallel like that. That's kind of, maybe they did do it elsewhere, and maybe I'm just wrong, and I could be. But wow, I'm a little confused on that. So I mean, you would think that the whichever one, there's always going to be one that's going to hog the current from the other one, but I don't know. Let me know in the comments. I mean, I'm not criticizing anyone. I'm actually questioning. I don't know. What do you all think? Is there a reason for this? Is this a viable option and it's good to do? You just don't see it? Or is this really something that kind of a little bit of a violation of, of our electronics rules? I don't know. Okay, I did misspeak about something here. I misspoke on the fact about this, on the original one being a single one. If you look in here, they don't show it, but they're saying BR3 and BR4. So they are actually showing 2 bridge rectifiers. They're just not physically showing them. In the second schematic for this, they're physically showing 2 bridge rectifiers. Here they just kind of, they're 2 components, but they're just showing it one time. And there's BR2 and BR1. The other thing I noticed is somebody has replaced BR2, which would be your plus and minus 50 volt rail, right here. And if we zoom down, man, is that a precarious job soldering those wires back on. This one right here is almost touching this track. I mean, just about. You can see it. I don't know if it's focusing, but it's very, very scary. When I check these out, these look to, the ones that I have that are replacements that are this physical size are all 2 amp. So they are very low current. So I think they probably needed closer to a 4 or 5 amp or 6 amp. So I'm going to see if I have some 6 amp bridges that are this size or close to it that I could replace this with. I don't like this. And then this one here, we at least need to come up with something to clean this up so this doesn't short out or cause problems. Alright, another problem I see is, so we have these 4 capacitors here, and these are 2200 microfarads each, and it's okay to gang up caps like this. Actually, when you do this, it reduces the ESR, because the ESR is like putting those the internal theoretical resistance in parallel, which will reduce the resistance. So this is a common thing to gang up capacitors like this. However, if you look at the voltage, this is a plus and minus 25 volt rail. So that means from here to here there's 25 volts, and from here to here there's 25 volts. And so you're applying 25 volts potential across each of these capacitors. And if you look at these capacitors, every one of them is rated right at 25 volts. That's a big problem. And the reason that's a big problem is because if you go a teeny little bit over, and remember, this is an adjustable power supply. It can exceed its rail voltage if you misadjust it. There's no room for error on this. So that is a really big no-no. These things are going to fail just by the component choice that was used. Now, here's what I'm going to propose to do here. The 2200s in parallel like this equal 4400 microfarads at 25 volts. I'm going to remove each pair and replace them with a single 4700 at 35 volts. And you can look physically, if you look at the size of these caps that I have, they're exactly the same case, same size. So by doing that, we're doing two things. Number one, we're giving a margin of error by having that extra 10 volts in there. It's a slightly higher but almost identical capacitance. These are pretty low ESR, high quality Nichicon capacitors, and they're 105 degree, so they're very high quality. And so safer, better suited to the circuit, and then by eliminating two of these capacitors, that's going to give us more real estate in here to put a bigger diode pack in here. I may even be able to fit a square one, kind of like this one, in here somehow, which will allow us to remove this bodge job back here and put something more reliable in there. Now, you may say to yourself, there's 6 capacitors, and that's because there's 4 on the 25 volt rails, and then there's 2 filtering the plus and minus 50 volt rails. Well, how are you putting 50 volts on a 25 volt capacitor? Well, again, nothing's normal in this thing. If you look, they don't reference the 50 volt rail to ground, but rather they reference it to the 25 volt rail. So the ground side of it, or the low side of this, is referenced to up here, and the low side of this is referenced to down here. So theoretically, for 50 volts, you'd have 25 volts potential here and 25 volts potential here. So you only need 25. But again, your capacitor is running directly at its maximum possible operating voltage, which is terrible. I mean, you don't do that. You usually, if you're going to put 25 volts on a capacitor, you would use a 35 volt capacitor. Now, you don't want to go too crazy. If I put a 100 volt cap in there, these caps may not stay formed properly, although that's debatable too. Just the keeping voltage on them all the time, you know, I believe keeps them formed somewhat. But again, that's, you usually, as long as you keep the voltage close to the, you know, a little bit above what your maximum voltage of the circuit will be, that's the best scenario. So 35 volt is what we should use in here. So again, I'll put some 2200s at 35 here, and that should take care of that. And then these ones, once again, we have plus and minus 80 volts on an 80 volt capacitor. So once again, these should probably be 100 volt. I mean, that's just the next size up from 80 would be 100 volts. So these should be, you know, 4700s at 100, which I do not have any of those. I may have to order one in. I may have one. I don't know. I have to look, see what I have. I have some things in stock. We'll have to see. But boy, we really got our work cut out for us, don't we?